Hey everyone, welcome back to the Incredible India podcast series.
It's great to be here.
I'm Sam, and joining me today is Taylor.
Hello, everyone.
So for today's deep dive, we're going into the scientific drama that literally put a subcontinent on the map.
We really are.
We're talking about the astonishing story behind the Great Trigonometrical Survey of India, and the most incredible part, this huge effort, which, ended up calculating the height of the world's tallest mountain, all started from one quiet, unassuming hill in Chennai.
It's a story of obsession, really, and geometry, and just sheer human endurance.
It's so much more than just cartography.
Oh, absolutely. When you look at the scale of this thing, the Great Trigonometrical Survey, calling it ambitious, is a profound understatement.
This was back in the early 1800s, right?
Early 1800s. And at the time, India was basically a giant question mark. Geographically, distances were just estimates, borders were fuzzy, and the true height of the Himalayas was basically myth.
The goal was pure precision then, to measure the exact length and breadth of the entire subcontinent using geometry. And that whole marathon started on a small hill called St. Thomas Mount.
Right, in Chennai.
If you go there today, it's actually a pretty peaceful spot. It overlooks this restless sea of the city.
Hard to imagine it as a scientific battleground.
But that's what it was. 2 centuries ago, that tiny hill was the 0 point for defining a huge part of modern Asia.
Okay, so let's get into the man behind it all. The architect of the survey, William Lambton.
Right.
His method was based on trigonometry, specifically something called triangulation.
Triangulation is, it's brilliantly simple in theory. Imagine you need to measure a wide river. You can't cross it.
Okay.
You measure one very precise short line on your side of the bank, let's say 10 miles. That's your baseline. Then from each end of that line, you measure the angles to a landmark on the other side, like a tall tree.
So you've created a triangle.
Exactly. And because you know one side's lengths, your baseline, and the 2 angles, you can use trigonometry to calculate the lengths of the other 2 sides. You've just measured to that tree without ever going near it.
And Lambton's genius was to just scale that up to a continental size.
That's it. He created this invisible web of triangles linking one point to the next, just creeping across India. But for that whole web to work, that first baseline had to be absolutely perfect.
Which brings us back to St. Thomas Mount.
Precisely. That's why it was chosen. Lambton needed a perfect scientific stage. The mount is a solid granite platform, stable bedrock. And it had clear, unhindered views across the coastal plain.
So no room for error at the start?
None. If your first angle is off by just a single arc second, that's 1/3600th of a degree, that tiny, tiny error gets magnified thousands of times by the time you reach the Himalayas. It had to be rock solid.
And the physical effort involved? I mean, the equipment they were using, it just sounds unbelievable.
We're not talking about compact digital tools here.
No. We're talking about huge theodolites, the instruments for measuring the angles. And some of them weighed over 500 kilograms.
Half a ton. And that weight was necessary for the precision. They had these incredibly fine scales made of silver or platinum designed to measure fractions of a second of an angle.
So the sheer mass was to keep it stable.
Exactly, to shield it from any vibration. Just hauling half a ton of delicate brass and glass up a hill, sometimes through jungle. It was an ordeal.
And then they couldn't even use it right away.
No, they had to build special stone pillars and wait weeks for them to settle before they could even start an observation. It was a kind of monastic patience.
So once they're finally set up, they immediately face another problem, right? The very air they're looking through.
That's when physics starts to fight back. Their biggest enemy was something called atmospheric refraction.
Which is basically light bending in the heat.
Yes. On a hot day, the air near the ground is less dense than the cooler air above it. So your line of sight, which you think is a straight line, actually curves upwards slightly.
So they weren't measuring a straight line at all.
They were measuring a subtle curve. Lambton's field notes are just staggering. He made them check every measurement at different times of day and then apply all these complex mathematical corrections for temperature, pressure, everything.
That obsession with rooting out error is what made it work.
It was everything. And from that rock-solid foundation at St. Thomas Mount, this geometric web began its slow crawl north.
But Lambton didn't get to finish it. He died in 1823, and the job passed to a man whose name is now, pretty famous, George Everest.
Everest, a very different character. Lambton was the innovator, the founder. Everest was the fiercely rigorous manager, almost obsessively disciplined.
And he inherited Lambton's work.
He inherited Lambton's southern triangles, But he knew that as the survey pushed thousands of miles north toward the Himalayas, the standards for precision had to be even higher.
So he didn't just continue the work, he basically upgraded the entire system.
Absolutely. He wasn't surveying from St. Thomas Mount, that part was done, but he revolutionized everything built on top of it. He commissioned bigger, more precise theodolites from London. He standardized everything.
But his biggest contribution was dealing with physics on an even deeper level, right?
Yes, he insisted on accounting for forces other surveyors had just ignored. Things like the Earth's curvature, and crucially, gravitational anomalies.
Okay, gravitational anomalies. What does that actually mean for a surveyor on the ground?
It means that gravity isn't the same everywhere. A plumb line, a weight on a string, relies on gravity to tell you what true vertical is.
Right.
But as the survey got close to the Himalayas, Everest knew that the enormous mass of the mountains themselves would exert their own gravitational pull.
Wait, so the mountain was actually pulling their instruments sideways?
Subtly, yes.
Yeah.
It was pulling the plumb bobs slightly off true vertical, just enough to throw the angle measurements off. And if your angles are wrong, all your height and distance calculations will be wrong.
That is an incredible level of detail to account for.
He had to apply these really cutting-edge mathematical corrections to every single reading to account for it. He understood that to measure the highest points on Earth, you had to understand the deepest physics of the Earth itself.
This was a decades-long effort, all driven by this obsessive discipline.
That's the legacy of Everest. He made sure that when the time came to do the final calculation, the data would be absolutely, unimpeachably trustworthy.
Which brings us to the final act. The foundation is laid by Lambton, the system is perfected by Everest, and now we get the aha moment.
We do. And for that, we have to go to the data processing office in Kolkata and to our final pivotal character, the Indian mathematician, Radhanath Sikdar.
So the surveying is done. Now it's about the math.
Exactly. The physical survey was only half the battle. By 1852, you have mountains of data angles, distances, and thousands of pages of corrections for refraction, gravity, all of it.
And Sikdar was the chief computer, is that right? His job was to make sense of it all.
His specific task was to take all that data and calculate the height of a distant Himalayan peak, which at the time was just known as Peak XV.
So he's not in the field. This is purely an office calculation.
A massive abstract calculation built on decades of work that started all the way back at St. Thomas Mount. The reliance on that initial accuracy is just enormous.
He had to trust every single number that came before.
He did. He had to apply every correction Lambton and Everest had logged. He couldn't just use the raw angles. He had to correct for the Earth's curve over hundreds of miles, for atmospheric density, for that tiny gravitational pull of the mountains.
And the outcome.
The outcome changed geography forever. Sikdar's computation, done with pencil and paper and trigonometry, showed that Peak XV was the tallest mountain on Earth.
Wow.
His initial calculation was 29,000 feet on the dot. They actually added 2 feet, making it 29,002, just so it didn't look like a round guess.
The accuracy is just astonishing. To do that with 19th century math.
It's one of the great feats of pre-digital calculation. Researchers have noted his result is extraordinarily close to modern GPS values. Think about that. The data was so good, his math matches our 21st century technology.
And that all goes back to the rigor started by Lambton on that little granite hill.
It's a direct line.
So if Sikdar did the final calculation, why is it named Mount Everest?
Well, Peak XV was named Mount Everest in 1856 in honor of George Everest. While Sikdar did the decisive math, the name was meant to recognize the leadership and the incredible technical discipline Everest brought to the whole project.
But the scientific lineage, the starting point that traces straight back to St. Thomas Mount.
Directly back.
Standing there today, it's so hard to imagine that this quiet hill, barely 300 feet tall, was the epicenter of something that defined the entire globe.
The original granite platform is gone now, swallowed by the city. But the legacy is still there. The precise coordinates fixed from that one spot still anchor India's modern maps.
It's an amazing reminder that huge truth can start in these small, seemingly unremarkable places.
It's all just relentless human effort. The mountain didn't move, but that little hill in Chennai finally helped us measure it.
This deep dive really makes you see a map differently. It's not just lines on paper. It's a monument to decades of obsession and calculation.
Exactly. And it makes you wonder, it raises a question for you to think about. This whole survey was started for military and administrative reasons, right? But the lines they drew, the facts they established,
Yeah.
did that map created with such incredible scientific precision, end up defining the political boundaries that maybe still cause debate in the subcontinent today?
A really provocative thought to leave everyone with: the lasting power of a line on a map. If you decide to travel to India, we have a recommendation. Five Census Tours organizes tours across India which are immersive cultural experiences. You can email contact@fivecenstours.com. Note 5 is written as a numeral in contact@fivecensustours.com. Or WhatsApp 2+919 845 677 446.